Welcome to chapter 3, part 1 video. This will be a chapter about exponential and logarithmic functions, which hopefully you have heard about before and are familiar with a little bit. And then a new function called a logistic function that we'll be talking about, not this video, but the next one. Okay, so today's video, we're going to be looking at a review of exponential functions and their graphs. We already started this review in class, looking at the natural base, which is called E, and then barely skimming the surface of population models. So why do we care? Exponential functions are a starting model for many growth patterns, including the growth of human and animal populations. So this is a great tool for looking at populations, for looking at endangered or extinct species, and looking at why those populations behaved the way they did. Okay, so let's start out with defining exponential functions. An exponential function has real constants, a and b, that are the two numbers that we can call the bases or the coefficients, okay? So the exponential function does not have a variable as the number that is the base or the coefficient, okay? X is in the exponent. That's what makes a function exponential. A has to be non-zero because if I multiply something by 0, it just turns to 0, and then we no longer have an exponent that is variable. And b has to be positive. We saw this a little bit in the exploration in class. If b becomes negative, then the function is non-continuous, okay? And then if b is 1, then that's no longer an exponential function, that's just a line, because 1 to any power is just 1. So a is the initial value, we call it the initial value, which means, remember, the initial value means that when we take f of 0, we should get a. So if we take f of 0, notice this would be a times b to the 0. Anything to the 0 is just 1. So this is a, that checks out. So the initial value is a, and b is the base. Okay, now bases hold things up, right? The base of the table is at the bottom. The base of the computer is the part that it sits on. So the base is the part that's holding up the exponent. Base, and we can call this the coefficient. Coefficient, okay? And the important thing, the very, very most important thing about exponential functions is the variable is in the exponent. That is what makes it exponential, okay? If I don't have a variable in the exponent, then I do not have an exponential function. We talked about this in class. If I have 2 to the x is exponential, x squared is a polynomial. Okay, if I had x to the 2x, which is what that actually looks like, that would be exponential. Okay, but just x squared is polynomial. Okay. So let's go ahead and look at kind of how the exponential functions behave. So in this example, we have a table of values, and we want to see if we can use this table of values to find an exponential function. So normally when we have a table of values, the first thing we look for is it linear? Is it increasing by the same amount every time? Now in this case, I've already written it out. It's not increasing by the same amount. It's multiplied by the same amount, okay? It has a factor that is the same between each term, okay? So when we're looking at, and let's focus on g of x first. So if we're looking at g of x, I have, notice here, when x is 0, this will be my initial value. That tells me that a equals 4. Remember, we said a is our initial value. When we have f of 0, or in this case, g of 0, we should get our a value. So we know that g of x equals a times something. Okay, now it's times 3 times 3 times 3 times 3. The number that's multiplied over and over and over and over again, that is our base. Whoops. A was 4 times our base of 3, and then this will be to the x, because if I multiplied this 1 time, I have 4 times 3 to the first. Multiply this 2 times, 4 times 3 to the second. I've got 3 and 3. So every time I increase my x by 1, I'm multiplying it by 3 again and again and again. Okay, now we can check this by substituting in, for example, -2. So if I wanted to check g of -2, I would say, okay, well, 4 times 3 to the -2. Negative exponent means it gets plopped in the denominator. That's 4 over 3 squared is 4/9, and that works. Okay, it's always a good idea to check your equations just to make sure that everything worked out okay. So let's see if we can do that now for h of x. H of x, we already know this is exponential because it was told to us, but also I'm multiplying by the same number every time. Again, I'm gonna look when x is 0, y is 8. So that gives me an a value of 8. This gives me a base value of 1/4. So we have that h of x equals 8 times 1/4 to the x. Let's test it out. Let's see what happens for h of 2. So this is 8 times 1/4 squared, or 8 times 1 over 16, which is 1/2. And that is what we got. Okay, so we've found our equations and we have tested them. G of x and h of x. Okay, so that's how we can find an exponential equation. Let's go ahead and define what's the difference between exponential growth and decay. We started playing with this idea in class, right? So for any exponential function where we have a as our coefficient, b as our base, and x is our variable, then if we multiply f of x plus 1, so we've gone one more x, that's multiplying it by b again. So remember we had f of x. If we go down, f of x plus 1, this was times our base. So that's what this says here. It says if we go down in our chart, if we move down by 1x to get our y value, we've multiplied by the base. And we're multiplying by the base every time. So if I moved down to the next row in my chart, this was my x values, this is my y values, this is x plus 1, x plus 2. Then to get to the next one, I would multiply by b again. So that's what that means, okay? If our base, okay, if a is positive, so our coefficient is positive, and our base is bigger than 1, then this is growth. So if our base is bigger than 1, this is growth. Okay. If our base is between 0 and 1, 0, whoops, I said I did that backwards. 0 is less than the base, which is less than 1. This is decay. And we're going to look at another way of viewing this in just a second here. I don't think the eraser worked. Let me try that again. Okay, we're going to look at this in another way here, but think about this. If my base was 1, that was my horizontal line, right? If the base is 1, we ended up with this kind of horizontal line just flatlining at 1. If my base is more than 1, then what happens is we end up with an increasing function. This is growth. If my base is less than 1, then we ended up with a decreasing function, right? This was the base less than 1. This is the base bigger than 1. But our base could not be 0 because if our base is less than 0, this was non-continuous. Okay, so those are our cases. Okay, we have our base bigger than 1 and our base between 0 and 1. And then we have our decay or growth factor, right? Factor being multiplied. So the growth factor is bigger than 1. The decay factor is between 0 and 1. Another way to look at this, okay, is to look at the rate of decay and the rate of growth, which we will do, okay? But first, let's look at these function transformations. So it's actually in a couple slides. So to transform functions, we're doing the exact same rules that we saw for our polynomial functions. If it's grouped with x, it happens sideways. If it's multiplied, it's a stretch or a shrink. If it's added or subtracted, it is a shift. If it's not grouped with x, then it goes up and down. If it's multiplied, it's a stretch or a shrink. If it is added or subtracted, it is a shift. So if we look at A, our first question is, what is changed from 2 to the x? So if I'm going to be making 4 graphs here. My basic 2 to the x just looks kind of like this. Goes through 1, and it goes, I should say, 0, 1, and 1, 2, right? For 2 to the x. You could substitute in and find that, but these are critical or anchor points for this function. For a, we have 2 to the x minus 1. So what has changed is that minus 1. It's grouped together with the x. So this should be a shift right by 1. So when x is 0, 2 to the negative 1, 0 minus 1 is negative 1, is 1/2. When x is 1, 2 to the 1 minus 1, that's 2 to the 0, which is 0. Nope, let's try that again. 2 to the 0 is 1. And then when x is 2, 2 minus 1 is 1, 2 to the 1 is 2. So we have here, it's same shape, but shifted over by 1. That point that used to be on the y-axis has now shifted over, and the point that used to have a height of 2 is now shifted over. For graph B, 2 to the negative x, okay? So 2 to the negative x grouped together with the x, so it's a horizontal transformation. This should be a reflection. Horizontally is a reflection over the y-axis. Okay, so again, let's try a couple of points. When x is 0, y is 2 to the 0 is still 1. When x is 1, 2 to the negative 1 is 1/2. And when x is 2, 2 to the negative 2, sorry, let's actually, not when x is 2, I wrote it where I wanted to, but I want to try when x is negative 1. 2 to the negative 1 is 2 to the 1, which is 2. Okay, so notice the graph reflected over the y-axis. Okay, and then finally, C, we have 3 times 2 to the x. This one is not grouped together with the x. It's separate from the x, so this is going to be a vertical stretch by 3. Let's test. When x is 0, 2 to the 0 is 1 times 3. Our y is 3 now. Let's test when x is negative 1. 2 to the negative 1 is 1/2 times 3 is 3/2. So notice we went from 1/2 to 3/2, 1 to 3. Let's do one more. When x is 1, 2 to the 1 is 2 times 3 is 6. So not only is this exponential, meaning it grows really fast, but it's also been stretched so it grows even faster. Okay, and this was our parent function. All right, so that's transformations. They work exactly the same way as our polynomial functions. However, now we just have to be a little bit more careful when we graph them and know what to expect. Go in with the expectation of the transformation. Okay, so E, this is a number, right? We talked about this briefly in class. Pi is a number, E is a number. So let's talk about pi for 1 second. Pi is approximately 3.14. So that means that pi is an irrational number, okay? Well, the same thing goes for E. E is defined as the limit as x approaches infinity of this function, 1 plus 1 over x, all raised to the x, okay? You don't need to know the formal limit of E for me, okay? It is used in calculus, okay? However, for me, you have your calculator. You can always double check E by hitting second, that's at the top left, second, and then right above the division sign, you should see an E. So if you use second division sign, enter, you should find that E is approximately 2.718. Okay, now that's a good approximation of E, right? But usually you only need to know the 2.7, okay? So for our purposes, if I say, what is the value of E, just tell me 2.7, because the important part is to know that it's between 2 and 3, closer to 3, okay? So when we're approximating things, we'll use E as about 2.7, okay? Now, almost always, you're gonna give me the exact answer by using just the E that's stored in your calculator, okay? And that will give you a more precise, if not perfectly exact answer. Okay, now why do we care about E? Well, E is called the natural base because it comes up a lot in natural calculations. Okay, so E is a number that just kind of like pi, every time you're calculating with a circle, it comes up. E comes up a lot when we're using exponential and related functions. Okay. So remember, I promised you another explanation for growth and decay. Well, if we're looking at this, we already talked about how growth means that it's going to be increasing, okay? And we said that the rate of growth would have a base, right? So if I'm looking at my rate of growth with a base E, E is more than 1. So we can say, okay, then my rate of growth here is base E. Because k is positive, e to some positive number x gives me a positive base. E, approximately 2.7, is bigger than 1. Okay, that would be exponential growth with a growth factor of 2.7. If we wanted to look at decay, we can also look at that with base e, but now we need e to be less than 1. So how do we get e to be less than 1? Well, we turn it into a fraction. So here we're looking at a negative k value. This is essentially f of x equals e times e to the negative something x, right? So now this is 1 over e to the x. 1 over e is my base. Oops. 1 over e, which is much smaller than 1. It's like 1/3-ish, okay? So growth has a base bigger than 1. Decay has a base between 0 and 1. Okay, so in words, what we just saw, when we have an exponential function, we can write that with the base e, with the natural base, okay? But because we're writing it with the natural base, our exponent can also have a coefficient now. When that coefficient is positive, e to a positive number x, then that will be growth. E to a positive number x. When that coefficient is negative, we have decay. That's e to a negative number x. Okay, now it could be negative 2x, it could be negative 1/2 x, but if the exponent is negative, that is decay. If the exponent is positive, that is growth. And that is only for when we have base e. Okay, that's specifically for when we have a base of e. And that way we have our growth factor, e, which is greater than 1, and our decay factor, 1 over e, which is less than 1. That's what we saw in the last slide. Okay, we can also relate growth and decay by their rate. So let's look at growth and decay rate. Okay, if we're looking at populations, we can say that a population grows or decays based on the rate of change. So if it's changing by a certain percentage every year, let's just say there's a population of mice and it grows by 20% every year. Okay, then its rate of growth would be 20% or 0.2. Okay, and when we model that into a function, we take the initial population or the population at time 0. That's p of 0, and then the p little subscript 0 means p naught or initial at the start. At the start. I think we've talked about this before. Okay, with the little subscript 0 means at the beginning. Then our first iteration, let's say it's the next day or the next week or the next month, but one iteration of time later, our population of after time 1 is going to be the initial population plus whatever the growth was. Okay, if we factor out p naught or p sub 0, notice that this leaves us with 1 plus r. That's going to be important. Okay, if we wait another amount of time later, now we're doing that same thing, but instead of P0, we have P1. Okay, but if we substitute that P0 in for the P1, then we end up with P0 times 1 plus R squared. Okay, so let's see if we can keep track of this. Let's say my initial population is 2, and I'm growing at a rate of 3. Okay, if, well, yeah, let's just say my rate is 200%. Let's say 200%. Okay, so I have 2 people, and those 2 people infect 4 people. And those 4 people each infect 2 people. So then 8 people are infected. Okay, so 2 people. The next day, those 2 have each infected 2. So that's 4 people. Now I have 6 people, but all 6 of those infected 2 people. So that's 12 people. Okay, well, I can write this as 2 times 3, or 2 times 1 plus 2. And I can write this as 2 times 9. Which is 3 squared. Okay, so now I have 18 people. They each infected 2 people. So that's 18 is 36, which is 2 times 27, which is 3 cubed. Okay, so notice every time everyone's infecting, I have the initial people who were affected plus the 2 more people that got infected. Okay, so if I start with 2 people and they each infect 2 people and they each infect 2 people and they each infect 2 people, we end up with this huge ripple effect. And that is what exponential growth is. But what I want to point out is these exponents here. So this was 3 to the first, 3 to the second, 3 to the third. Okay, and where does the 3 come from? Well, our rate was 200%, which is 2, plus the initial, right? I had an initial population. 100% of my initial population was in my study. Okay, now this can be growth. It could be like having babies. Okay, or it could be the spread of kindness, right? Relating to the advisory that we had. Every kind action causes another kind action, right? So if I am kind to 2 people and each of the people I'm kind to are kind to 2 people, then that infection of kindness spreads, okay? And what we end up with is this formula of whatever initial value we started with. So our initial value was 2 times 1 plus our rate as a percent. So if 200% as a decimal is 2.0 or 2.00 plus 1 for the initial percentage. So this is 100% of the initial population plus the rate, all raised to how much time we give it. Okay, so that's just a pattern. But notice now my base is 1 plus a rate. So the base that determined the growth or decay is now written as 1 plus a rate. Okay, so how does that relate to decay and growth? Well, if we look at an exponential population model, using that formula that we just derived, using this formula here, if we express the rate as a decimal, we can say 1 plus r is going to be greater than 1 when r is positive, and it's going to be less than 1 when r is negative. So if I have a rate of growth, I add it. If I have a rate of decay, I subtract it. So if my base is greater than 1, then my rate is positive, and this is growth. If my base is less than 1, then my rate is negative, and this is decay. Okay, so that kind of pulls everything together, our rates of growth or decay. So let's look at this population model. We have a population. It starts out as 786,543. It has a base of 1.021 raised to the t. Now, it doesn't matter if we use t or x, it's raised to a variable. Okay, so we know it's exponential because it has a variable in the exponent. This first number, the coefficient, this is our initial value or our initial population. And this base right here, that's what I want to look closer at. The base is 1.021, which is bigger than 1, so we expect that to be a growth. But what percentage has this grown by? Well, we also know that 1 plus r is the base. So 1.021, subtract 1 from both sides, then our rate is 0.021, which is 2.1%. So we've just said that this equation represents a growth of 2.1% because the base was bigger than 1. Okay, that is it for this lesson. So we're going to pick up from here next class, talking about population models, and then we're going to kind of introduce logistic functions as a new way of modeling populations. If you have questions, please reach out to me. Otherwise, I will see you in class.